How does the atomic clock play a role for deep space navigation? Well, today, atomic clocks are central to deep space navigation. It's just those clocks are on the ground. And so an atomic clock generates a signal and is sent through the antenna on the ground to a spacecraft in deep space. And that signal is turned around and received back at the transmitting station. And with that transmission of a signal, we can do measurements of that signal. You know, how the Doppler shift on the signal is a way in which we can determine how fast the spacecraft is moving, and how long that signal takes is a measure of how far away that spacecraft is. So the deep space atomic clock can change that paradigm. You can originate the signal at the Earth, and it can end at the spacecraft. It's good enough that small clock that we're building is as stable and accurate as the ground clock that originated the signal. We get to utilize some of the efficiencies that the Deep Space Tracking Network has to offer today. The DSN supports more downlinks than it does uplinks. And so at places like at Mars, where we have a number of spacecraft that are competing for two-way tracking time, you don't have to do that anymore. Well, what does that do for us? Well, what we've found that with a 2 times increase in our tracking data for a Mars orbiter, the orbit information that we get is improved upon by a factor of 5. One of the things that we're envisioning at Mars is landing a pinpoint lander, one that can land to a very precise location on the surface of Mars. And there's a lot of steps to making that happen, one of which is entering the top of the atmosphere and taking your entry state knowledge and on board flying a trajectory of that entry state knowledge. Well, the way in which we upload that navigation state today is we do all the processing on the ground, and about 6 or so hours before entry we upload a final nav state to the vehicle. Well, you can imagine after 6 hours of flight that that solution is a little stale when you get to the top of the atmosphere. Well, with DSAC, with the measurement happening on board, you don't have to suffer that 6-hour delay. You can be computing on board in real time, and what that does is where the 6-hour solution is in error by a few kilometers, this solution that's on board is only in error by a handful of meters. And that has a real benefit to decreasing the amount of propellant you got to carry to then later fly out the errors that you originally had when you didn't know where you were at the top of the atmosphere. And so that's going to open up new ways of new science that we're going to be able to do. In fact, it's going to improve the gravity science that we are able to do at Mars today. An example of gravity science improvement that the clock enables further out is NASA's envisioning going to Europa, a moon around Jupiter. And one of the fundamental things we want to learn about Europa is if there's an ocean underneath the crustal ice that we see at Europa. Well, gravity science is a way in which we could make that determination if there's an ocean underneath. And to be able to do the measurement, the gravity science measurement that NASA's planning, they're going to do it, one approach is in a flyby mission. So they'll fly by Europa with a 4-hour tracking pass and then have a 30-day orbit around Europa and then come back for another flyby and do a sequence of 30 or so of these flybys. Well, if we have the atomic clock on a downlink signal from that flyby and it's received at the Earth, we can do it at Ka band. And the benefit of going to Ka band isn't so much that it has to deal with we can increase the bandwidth, but what it does do is it improves the accuracy of the measurement that we're taking. And it improves it by an order of magnitude, and that's fundamental. It's that improvement in the data quality that will allow us to determine the gravity well enough to determine if there is an ocean underneath.